Hey there. How I hope you're doing all right. Today we'll be jumping right in to the problem of support vector machines and this absolutely rather elegant algorithm that we have. We're gonna today talk about linear SVMs. That too for two-class problems, and then we'll not today, but in the future, we'll go on to more and more difficult problems, I suppose. So imagine, let's jump right into it. The idea is we'll cover the geometric intuitions of this problem, then jump into the optimization problem, and that should be, and then ultimately what leads to the classification. So I already have this really gutted image, I suppose, but I'm gonna rehash it whenever possible, right? So let's say we have w1 x1. Sorry, let me take a step back. This is a general line of the equation f, and for the uninitiated, this can be represented as x plus by plus c. But machine learning notation suggests otherwise. We have weight vectors and biases, and that's why it looks like this. Correct. Right. So this vector w, the weight vector, where w is equal to w1, w2, is actually perpendicular to the normal line. B is a constant offset, like you have an intercept. So the interpretation where we go is the usual interpretation of. So this is more of a mathematical convenience. Any straight line 2D or plane 3D or hyperplane would be more than 3 dimension, can be written as a coordinate of a combination of coordinates plus a constant term. The sign this wx plus b tells us which side of the boundary x resides on. More or less, the decision boundary looks like wx plus b greater than 0 if the point is on one side, this side, essentially the positive plus one side. If point on positive side, wx plus b would be less than 0 if point on, which is on this side, and wx plus b is equal to 0 if the point exactly is on the boundary. Amazing. So in speaking in classification terms, so predicted class x would have a sign meaning positive negative wx plus b. I hope this is clear by now. In this case that we've discussed so far, our data is linearly separable. Let me draw it again. Let me just draw it again. I'll just if it. So this is our feature space. There's some data points. So as you can see, our data is linearly separable. So if you draw a line, we'd get a training error of 0. Similarly, but if you get this line, if you draw this line, you'll also get a training error of 0. Same with this and same with many other lines. So in theory, there are infinite lines which you can draw, right, wherein you'll get training error. But the problem here is we do not know which one is the best. So the answer of the SVM, like what SVM tries to do, is like we selected the boundary which maximizes the margin. So we take this line, let's say, imagining holding it and pushing it parallelly towards both the negative class and both the positive class. So something here and something here. right? We want to maximize this margin. And the first data point in either class which touches these boundaries is called a support vector, right? Uh, Again, so these the premise of SVM is only these points matter in determining the final boundary. All other training points which are like further inside do not affect the optimal solution once the boundary is locked. I mean, वहाँ पे जाएगा और जैसे छुएगा, that's it, right? Now, say we want to derive the margin distance. Like how do you want to do that? Like, okay, let's derive, because this will set up us for our optimization problems, right, going forward. So we have wx plus b, right, equals to 0, and we have two parallel hyperplanes. Oh my god, sorry. For this is for the positive class and this is for the negative class, and this is, it's not positive negative as such, but class is on the right and class is on the left. And for mathematical convenience, we introduce that it assumes a positive class if wx plus b is equal to 1 minus otherwise. This is convenience, by the way. कोई रामानुजन की तरह माता आके नहीं बोल गई आपने कैसा करना है, but it will make things easier for us in the future, right? So if you do remember your geometry, and this is more specifically distance to a hyperplane, in this case is perpendicular distance, right? सोच के देखो कि इसको इसके और इसका डिस्टेंस क्या है, तो दिस इज अ परपेंडिकुलर डिस्टेंस, राइट चमका? तो वी गेट द डिस्टेंस d from point xo as follows. एंड इफ अगर याद हो तो दिस इज कॉल्ड यूनिट नॉर्मल, राइट? ऐसे भी लिख सकते हैं उसको, पहला सोचा हो तो इसको यूनिट नॉर्मल वेक्टर बोलते हैं. Oh shit. Okay. For a support vector x positive, I'm going to on the +1 hyperplane, मतलब on the right side of the things, the distance to main boundary, if you remember, इसको positive दिया था, is 1 for d plus, and for d minus it also is the same, right? Because this is a modulus function, and negative b will get a positive answer. So finally we get a margin which looks like this. A lot of dog problem in Bangalore for some reason. So we want to maximize the margin. So maximizing the margin is our goal. But that is the same as minimizing this, right? क्योंकि इमेजिन करो कि अगर ये बहुत छोटा होगा तो ये एनीवे मार्जिन बढ़ने वाली है. Or similarly, for calculus purposes, again, this is a mathematical convenience, right? So because it's more differentiable this way, if you take the trivial power law here, you'll see 2 and 2 cut हो जाते हैं, and we'll finally get again the same thing. So we also minimize. We usually do this. This is a minimization problem. And before we step into the, I guess, the more crux, or I think the more tougher part of the problems, let's define constraints. So along with maximizing the margin, we also need each point in class -1 or +1 to be on the correct side of its bounding hyperplane, right? That is our whole premise this is based on. So if yi is equal to +1, we need to enforce the constraint that wxi plus b is also greater than +1. Similarly, if yi is negative, we enforce correct. But if you combine these, right, because if you multiply yi with this one, which is also already negative, this will turn positive, and this is already positive. So we can combine this constraint because it's easier to carry just one constraint instead of like satisfying two constraint and then mathematically solving. So we get this. For all I, for all I, right? Now our primal optimization problem looks like this. So minimize these subject to the constraints that I have defined. Where m are the number of training samples or ordered pairs of xi's and yi's. Now, but this is not the final optimization problem, because it's not a trivial optimization where I just trivial optimization with this objective function. अगर ये होता तो I could have just set this equal to 0 and solve for that and get receive the answers. But the problem here is we have multiple constraints, right? Therefore, we need a systematic way to solve or to optimize, bearing in mind the constraints that we have. So that therefore it's imperative that we introduce something called Lagrangian, right? Okay, so before I formulate the Lagrangian problem with respect to this SVM problem that we have, I want to spend some time discussing what Lagrangian is, okay? Because I'm assuming here not many people might be familiar with it. So it's prudent to spend some time here. So Lagrange multipliers more broadly. We use a Lagrange multiplier alpha I greater than 0. So in general, let's say we have to minimize a function which has parameters to a different function which assumes a value of 0 or above, right? So our Lagrangian would solve for everything, would take into account all the things. And here we're going to sum over I, because the constraint is applicable for every training data point, right? Again, we use Lagrange multipliers just because there are multiple constraints we need to handle, and we cannot just optimize for either the constraint or the function. If we just optimize for taking a little digressing for a bit, but if we just solve for this, right? If we just optimize for this, right, we'll have no idea what is the governing or the guiding principle of where to take the line is, right? We'll just be solving the constraints respect to the weight vector and the biases vector, and we'll be fulfilling that only without ever knowing कि भाई लाइन का क्या करेंगे, लाइन आगे बढ़ानी है, कम करनी है, जो भी है, right? So in that cases where the constraint is applicable for all the training samples, that's why I summation, we add a multiplier, a non-zero multiplier by the way, to this, to the constraint. This is the constraint in this case कि 0 से बड़ा होना चाहिए, and again this is non-zero also. So if this is violated, let's say this constraint is violated, right? Gi is, let's say, assumes a value of less than 0. Large AI increases like Lagrangian and penalizing that solution, right? If G is satisfied, if this is satisfied, then this is also controllable. So it also takes into account that. That is why it assumes a min max formulation. But before that, this is what the Lagrangian in case of SVMs look like, right? This is general formula, okay, for SVM. So for SVMs, it looks like the following. Again, we have the same setup more or less, and this is our objective. This is what we want to minimize, if you remember. Again, the similar constraint being held that this is greater than 0. So if you see, there is a min-max constraint that we are looking for here. We want to maximize this and we want to minimize this, right? So we are looking essentially for a saddle point. So this is what our optimization problem looks like now. Sorry. Cool. Now let's solve the Lagrangian now and see what we get. So we, to find the optimum weight vector biases and I mean AI, alpha, I should not say AI, right? We impose the Karush-Kuhn-Tucker conditions. So these are a bunch of steps or conditions which are like, there are 4 conditions. I cannot recollect exactly, read about it in my master's days, but essentially these are like step-by-step conditions you must fulfill to get to the optimum, right? Now we're just taking a derivative. Now let's just I'm going to rewrite it, and then we're going to take a derivative, partial derivative rather. Cool. Now I'm going to derivate this function with respect to w. Now seeing this 2 नीचे आ गया, we'll get this w minus this is this won't count, this won't count, this is a constant, this will be treated as a constant. So alpha I yi xi, because w again, so yeah, cool. So we get w, sorry, equals to 0. So we get w is equal to summation I equal to 1 to m alpha I yi xi. Cool. Now we also need to derivate it with respect to w, the bias, sorry. This would be 0. Again, it doesn't contain a b, doesn't contain a b. This contains a b, तो yi alpha I yi b, if you can see it from here, alpha I yi b ये constant है. Sorry, इसमें b नहीं है तो constant है. ये भी, it also won't contribute. So what we'll get finally is going to be something like this. ये माइनस साइन ऐड करते हैं, then alpha I yi, right? Setting this to 0, we get ये फुलफिल हो गया. So now, okay, there's some more space. So what KKT conditions include, right? It includes that the primal feasibility, matlab the initial constraint condition of yi times w plus xi times w xi plus b minus 1 is always equal or greater than 0, and the dual feasibility, where is this value is always greater than 0, and the third, which is something called slackness or complementary slackness rather, and this is, I think, where the magic happens, right? So it looks like the following: the combination of primal duality and primal feasibility and dual feasibility. You can think of it in that way, right? So this implies that this term is only greater than 0 when this is equal to 0, right? So when point xi is on the boundary, मतलब अगर xi boundary पे होगा, like if xi is on the boundary, this would be 0 as we talked about previously, right? uh, and therefore this would be non-zero, this can be non-zero essentially. uh, this has to be non-zero, right? So only these would be importance as you discover, because these are the support vectors, because these are the only ones, the only alpha is which matter, right? So we can substitute the values now. Yeah, that's that. Now we can substitute the values of w and uh, back into the Lagrangian, and we obtain what's called the Wolf dual in terms of alpha. So it's a convex quadratic program which can be solved, and most alpha I will become 0. The only non-zero ones which support, as I said, correspond to the support vectors. So once we solve, let me just not write it here. So now let's substitute the values of w and b back in. Well, yeah, and after that we'll talk about how it classifies, and that will be, I suppose, the end. So we discovered that we just have to take the square of it. So we found the value of w, alpha I, y I, what was it? Xi, right? Sorry. And twice that. Minus alpha I, y I, xi. Sigma alpha j, yj, xj minus alpha I, yi plus b plus alpha I. Now this, if you know, we would derive that this goes to 0, right? When we solve for b, this will come out because it's a constant, and the final equation would look like, which we want to optimize. Oh, sorry, half there. Minus half I j, all of them going for 2m, right? Because of number of training samples. So alpha I, alpha j, yi, yj, xi, xj. So this is our final optimization problems, which can be solved as I discussed with the QP solver, or like it's a quadratic programming problem. So it's a can be convex programming problem, and can be solved by QP problems. Now decision, as I've said, decision time. Now how does classification happen? So once we've solved for it like this, when you optimize this, when you solve for alpha I, we get w so I only belonging to the support vectors, alpha I, y I, x I, because these are the non-zero ones. The rest, as you recall, have all been zero. So essentially all you get, the alpha is, would correspond to support vectors, and yi is equal to 0, right? So classification of a new point x new would be sign, right, positive, negative, plus b. So if you see, this is the sum over only the support vectors, right? And this is how the classifications happen, and this is how they're only contingent upon uh, the support vectors. Cool. I think that does it. um, thank you for watching. And just for summary, I'm just gonna take a few moments of yours to just discuss. So the original problem that we started with, we had linearly separable data, and we wanted a best fitting line or a hyperplane, right? Now, when when two classes are perfectly linearly separable, we want to ensure that this generalizes for any test data point and gives us a very robust, I guess, a model. And that's how we formulated as that predict class will have a sign, but if this is on the right side of the things, it will have a positive sign, negative otherwise. Similarly, we formulated the decision boundaries, and we set these to positive one and a negative one, just because just how we discuss. So the decision, if you take the normal vector, like when you take the width and multiply it to the normal vector perpendicular, so you get for this value on the positive side, you get 1 by the norm of the Euclidean norm of the weight vector. Similarly, you get for the negative class or the left side of things. Therefore, we get a margin, and we want to maximize the margin, which is equivalent of minimizing this, or minimizing the half times squared Euclidean norm. The constraint we have defined as y I assume positive, plus 1, this should be enforced, and yi negative, this should be enforced. To combine them, we come up with a single constraint which is applicable for all i's. The primal optimization problem therefore becomes minimization of weights and biases with respect to this half times square root of Euclidean norm, subject to the constraint described subject to the constraint yi times wxi plus bias, which has to be greater than or equal to 1, holding for all the training samples. Now we discuss why we need Lagrange multipliers, because there are multiple constraints, and for every data point we have a constraint. Therefore, we set that up. We use a Lagrange multiplier alpha I, which is non-negative, and then we set up the problem as a min-max problem or a saddle point problem, because we have to maximize alpha and we are looking to minimize the weights and biases. Setting the weights and biases, we get the following equations, which you simply plug in to get the final optimization that we need to do. And as you can see, the only alpha is, because of the complementary slackness, the alpha I, which will be non-zero, will be the support vectors. The rest will be all turned to 0. So for new classification point, it will only sum for problems which are support vectors and not for any others. So this is our final classification, right? That wraps up this lecture about hard margin support vector machines. There is also, in real world, there is something called soft margin support vector machines, but I would like you to read up on more than that. This is that deals when it's rather tricky to separate two classes, and therefore they introduce a third variable which accounts for that, and it allows some leeway for these classifiers. But otherwise, this is an amazing algorithm. I hope you enjoyed it as much as I did making it. Good luck, and I'll also drop in for the more curious. I'll also have that recommended book for convex optimization problems for those who wish to do it, because all of these Lagrangians and convex optimization problems will be a part of it, so it will be a nice exercise to do. Anyway, cool. I hope you enjoyed it, and thanks for watching. See you.